So today we are basically going to start with real functions. We're going to know what real functions are, and we know the definition of a of a function to be a rule which maps real numbers to real numbers as well. So the real numbers on the left hand side is going to be the domain. So you're going to have your domain, and you're going to have another set of elements too on the right hand side, which is going to be the elements in the codomain as well. So that's basically a real function. It's a rule that maps elements from the domain of real numbers to a codomain of real numbers as well. So under real functions, we have to know the nature of these real numbers. Okay, we want to know the nature of these real numbers. We want to know what the real line is and how it is, like what it really does, and what are some of the terminologies you are supposed to know under under the real numbers. Okay, so first of all, we are going to talk about I picked the real line. So this is my real line, starting from negative infinity to positive infinity. Okay, I can pick any 2 points within the line. So this is my point A, this is my point B. Okay, yeah. So what I'm actually trying to say is that if I'm going to pick an open set, okay, an open set from this point A to point B, I'm actually talking of the elements within this set here. That's what I'm talking about. I'm talking about these elements, and this is actually equal to any element S such that you have A being less than the S and at the same time being less than the B. Okay, so it actually means that when I pick any element within this set, I'm going to have a number which A is less than it, and at the same time is less than B as well. So that's the first definition we are supposed to know about this. And when looking at this line over here, we can actually see this as an interval. Okay, it's an interval. Okay, so now let's define what an interval also is. This set we have here, A, B, right? It's an interval. From this point to this point, it's an interval within the set of real numbers. And what we are going to call an interval in this real functions is that when I pick any 2 points within an interval, there should be another element which is in the whole interval. Okay, so this is my AB, this is my interval I'm calling. Then if it is an interval, then it means that when I pick 2 points within AB, which are these two I'm picking, I can get this element within it, and this element should also lie between A and B. Okay, so that's the definition of an interval. Okay, so an interval of any domain or any field is said to be an interval, or you have 2 points, like an open set to be an interval, provided that when you pick any 2 points within that open interval, the elements there are also found in the interval. Okay, all right, so that's it. Then the last one, we're actually going to talk about countable sets and finite sets. So we know countable numbers, or count numbers, or natural numbers. Okay, so natural numbers actually start from 1, 2, 3, 4 up to infinity. Okay, so these are natural numbers, and if any set shows this behavior, all right, looks like this, then it is also said to be countable. All right, so an example could be 1 out of 1, which gives you 1. So let me clean this and make it 1. Hold on. So 1 out of 2, 1 out of 3, 1 out of 4 going. So you can actually see that these are not natural numbers except one, okay? But these are not natural numbers, but you can actually see that there is this kind of one-to-one correspondence between the two sets, okay? So since this one is in one-to-one correspondence with that, it is also said to be countable because this is countable, okay? So that has to be countable. All right, yeah. So that is what a countable set is. So if any set is in one-to-one correspondence with the set of natural numbers, or it is in one-to-one correspondence with a subset of the set of natural numbers, it is also said to be a countable set. Okay, yeah, so that's a countable set. Now let's move on to the last set we are going to talk about. Basically here is the finite set. So let me take this set of natural numbers and try to make it finite. So if the set of natural numbers, I know it starts from 1 up to infinity, but if I have 1, 2, 3, and then that's, let's say, 10, then I know the end points of this set. I know when it's going to end, and it's ending at 10, right? Yeah. So once I know the end of this set, it makes it finite. So we actually know that every finite set has a beginning. We know the beginning not to be negative infinity, and we know the end not to be infinity. We actually know the actual numbers beginning and the actual numbers ending. So that is a finite set. So if I want to define what a finite set is, then, we're actually using the set of natural numbers, a subset of the set of natural numbers over here. But also, I'm not going to use the set of natural numbers or a subset of them, but I can have something like 1, 1 on 2, 1 on 3, getting to 1 on 10. I don't have a set of natural numbers over here, okay? Apart from 1, these are not natural numbers. Yet, I call this a finite set because it is in one-to-one correspondence with this set, or it is equipotent to that set. So when I say equipotent, it means there is a one-to-one correspondence, or between the two sets. Okay, so you can actually see that this is ending at 10, which means there are 10 elements. And even though this isn't a set of natural numbers, it also has 10 elements. You can count them and you know the number, so it makes it finite. Okay, yeah. So to define a finite set, you say a set is said to be finite, or a set E is finite, if there exists there exists a natural number n, okay, such that it is equipotent to 1, 2, 3, 4 up to that n. Okay, so every set is said to be finite if this rule is satisfied. Okay, so there is always this natural number such that the set E is in one-to-one correspondence with that. So if my n is 10, then it means E has 10 elements as well. If my n is 5, it means E has 5 elements too as well. So that's the definition of a finite set. Okay, so with this kind of set, the countable sets, you can actually see that it has a beginning 1 and has no end. So if I can actually count these but do not know the end of the set, then it becomes countably infinite. So this is a countably infinite set. Okay, so this is a countably infinite set. The set of natural numbers is a countably infinite set, and you can actually see this one is also in one-to-one correspondence with that. So it actually means this one is also infinitely countable, or it's a countably infinite set. So any set which is in one-to-one correspondence or is equipotent to the set of natural numbers is said to be countably infinite. Okay, yes. So these are some basic definitions we have to know, and in our next video we are actually going to delve deeper. We are going to talk about the open set, the closed sets, and we can start serious business. So see you in the next video. Thank you.